All right, so this is Math466, Advanced Applied Analysis, Lecture 9. So what we're going to do today is we're going to prove Poisson summation. And in the course of proving it, we're going to talk about why we make the assumptions we do about functions and what is the right thing to look at. So right now we've done Fourier analysis on an interval, either minus a half or 0, 1, something like that. What we're going to do now is we're going to look at generalizations of the Fourier transform that will apply to the entire real line. So Fourier transform. So g hat of y is the integral from minus infinity to infinity of g of x e to the negative 2 pi I xy dy. So there's a couple of things to note from this. The first is that the Fourier transform, I don't evaluate it just at an integer, I evaluate it at a real number y. Second is the interval is now minus infinity to infinity, so we have to worry about whether or not the integral converges. There are at least 3 different definitions of the Fourier transform. You can have a plus sign here, you can have a minus sign here. That's 2. And then some people don't like the 2 pi, so you can remove the 2 pi if you want. Some people put a square root of 1 over 2 pi outside to try to skirt the 2 different camps about where the pi should be. So there's a couple of different choices you can make as to how you want things to be. So the first question you should always ask when you see an integral is what? Does it converge? And so what you would get as a nice result is g hat of y in absolute value is at most the integral from minus infinity to infinity of absolute value of g of x dx. Because the exponential e to the negative 2 pi I xy is going to be 1 in absolute value. So if g is in L1, it exists. So exists if g is in L1 of R and bounded by the L1 norm of g. Okay, so the object exists. The main goal for today is to prove the Poisson summation formula. I am going to be a little bit vague. I'll say the following. If f is good, then the sum n goes from minus infinity to infinity of f hat of n is the same as the sum n goes from minus infinity to infinity of f of n. Is that basically you can just drop the hat if you do this type of sum. This is an amazingly useful result. When we do Benford's law, we will be using this to do a lot of the analysis. Now, clearly there has to be some conditions on little f for this to make sense. We have infinite sums. We need to have the sums converge. So we're going to need to assume some type of decay properties. Okay? So I'm going to do some notation first. Have we done big O notation in this class? All right, this is good notation to be at least aware of. Big O or less than less than. We say f of x is big O of g of x if there exists an x0 and a c such that for all x greater than or equal to x0, f of x in absolute value is less than or equal to c times g of x. And we also write this f of x less than g of x. So what this is saying is that from some point onward, the relative size of f and g has to be such that if you multiply g by a constant, you're larger than f. So let's do a few examples. X squared is big O of 1/2 x squared. Is it true for all values of x that x squared is going to be less than or equal to some constant times 1/2 x squared? What should we take the constant to be? 4. And then we're safe. We could take the constant to be 2 and we'd be safe. x is big O of 1/2 x squared. When x is very, very large, x squared beats x. If x is small, however, x is actually larger than x squared. So it could take a while for things to kick in. X to the n is big O of e to the x for any n greater than 0. There's a lot of ways to see this. Probably the easiest way to see this is, without loss of generality, we can assume n is a positive integer. If not, look at the ceiling of that. And when we look at e to the x, it has the term x to the n plus 1 over n plus 1 factorial. And that's going to be x over n plus 1 factorial x to the n. So once x is larger than n plus 1 factorial, this will beat that. So this tells you that a polynomial is going to grow slower than any exponential. Log of x to the n will be less than or equal to x. And one way to see this is I could let maybe x be e to the y. And if I do that, then this becomes y to the n, big O, versus e to the y, which we just proved over here. So whenever possible, you always want to reduce things to things you've already seen. Okay? And then the last one is, I think I want to use decays like x to the alpha. Okay. So we say f decays like absolute value of x to the negative alpha, alpha greater than 0, if f of x is big O x to the minus alpha. It might decay faster than that, but just from some point onward, it's decaying at least as fast as this. What do you think would be really nice for alpha to be? What size do you want alpha to be? Now I'm saying alpha greater than 0, but maybe I want something stronger than greater than 0 to be useful. Any thoughts about what size we would want? Greater than or equal to 2. You could actually do a little bit better. Greater than 1 would be fine, because we don't have to have alpha be an integer. Often want alpha greater than 1. And that's just going to give you better convergence properties. I can then integrate that, and I'll be fine. If it's 1 over x squared, absolutely fine. But 1 over x to the 1.1 would also be sufficient. Okay. So now what we want to do is we want to start looking at, well, slowly moving, but it did move. We want to start looking at good functions. So right now, we know Fourier analysis on the interval 0, 1 or minus 1/2. I'm now introducing the Fourier transform, which is on the whole interval R. So the idea is we want to somehow convert these problems over the entire interval to a problem over the finite interval 0, 1, because we understand the finite interval 0, 1. That's the meta idea behind today's lecture. How do we somehow convert to something we know? Well, let's say f is nice. Consider f of x is the sum and goes from minus infinity to infinity of little f of x plus n. What can you tell me about this function? So what would be true about this function? Any thoughts about nice properties? So we're talking about trying to get something on 0, 1. So what values of x would I use as inputs? I'm sorry?
Should you put in 0?
So I could put in 0. So if I put in 0, I just get a sum of f of n. What other numbers could I put in as inputs? I mean, I can choose any value of x. Do I have to understand this function for all values of x? Which values of x do I need to understand this for? 0 to 1. Why don't I need to understand what's going on at x equals 3/2?
What's nice about f? Is it periodic?
Well, right now, I'm just saying f is a nice function. What would be true about this function? So assume the sum exists. I'm not assuming little f is periodic. What about big F? Do you think big F is periodic? Big F of x plus 1 would be the sum. I'm sorry? Well, that means no matter what value of x you put in, you get the same value. If I put in x plus 1, I'll get f of x plus 1. I'm sorry? Big F is going to be periodic. Because as n ranges from minus infinity to infinity, what does 1 plus n range over? 1 plus n is going to also range from over the integers from minus infinity to infinity. So this is the same as maybe m goes from minus infinity to infinity of f of x plus m is f of x.
So it's periodic on any interval?
So f is periodic. It's periodic with period 1. So big F has period 1 if it exists. It may not exist. Maybe it's identically plus infinity. You know, imagine the function f is identically 1. If the function f is identically 1, this function is identically infinite. So in order for this to make sense, I need this sum to converge for any choice of x. So if I assume some kind of decay properties of f, then I'll be okay. So if f decays like x to the minus alpha for some alpha greater than 1, then big F exists. Right? Because now this sum is going to be fine. I can deal with finitely many terms, and then the terms in infinity decaying like 1 over x plus n to a power greater than 1. So it's going to be like 1 over n to a power greater than 1, so it'll be fine. We have to be careful. It is possible that the function might not exist. So, you know, as an example of a dangerous function, let's take, here's n, and what we can do is we can choose our function to spike up at n over a smaller and smaller window. So let's have this window over here be of size 1 over n, and let's have this height be 2n. So if we look at the area under this curve, each one of these is going to have area 1. If I look at f of 0, that would then be the sum from minus infinity to infinity. We'll assume here that, you know, n, we'll just do this for n greater than 0. So this would be a sum, n goes from 1 to infinity, of just 2n. So this function would blow up at 0. In fact, it will blow up at any integer. If you choose anything other than an integer, however, it's fine. Imagine you choose the point 1 over 20 quadrillion. Well, 1 over 20 quadrillion is going to be very close to n for quite a while, but eventually 1 over 20 quadrillion will be separated enough so that this band of length 1 over n is so small that you're outside. So as long as you don't evaluate this at an integer, you're fine. But if you evaluate this at an integer, you can...
Yeah, I lost you there.
Okay, let's say you look at x as not an integer.
Yeah.
let's say x is 1 over 1,000.
Sure.
Then this is a band of length 1 over n, so it goes from n minus 1 over 2n to n plus 1 over 2n.
Sure.
So eventually, if I look at 1,000, 1 plus 1,000, 2 plus 1,000, 3 plus 1,000, 4 plus 1,000, eventually it's outside these bands.
Yeah.
And so then the function would just be 0 at that point. And so when I looked at evaluating big F, if I evaluate big F at any place other than an integer, I only have finitely many terms. And big F would have a finite value.
So there are these spikes at every n?
At every n. So as you march down, so the next spike at n plus 1 would be a little bit higher and a little bit tighter. And then over here at n minus 1, it would be a little bit smaller and a little bit wider. So you march down at each one of these, you have a spike. So the problem is the function blows up at one point. 0 or all the integers. And every other place it's fine. We need to avoid something like that. Does this function have the decay we want? No. This function is not decaying like x to the minus alpha. Because in fact, it's going off to infinity along a subsequence. So the difficulty when we're looking at something like this is we need to make sure our function big F exists. So we need to put some constraints on little f for this function big F to exist. If we assume little f is decaying, then we're OK. All right. We know big F is periodic in 0, 1, or minus a half. Because we know it's periodic, what should we look at? Yeah, we should look at its Fourier series, right? So the goal is to try to see why these are natural things to look at. So we'll look at the Fourier series. Whose theorem do we want to use? So we'll look at the Fourier series. So whose theorem do you think we want to use? We've got two big theorems. So Fourier would then be looking at the weighted Fourier series. So if we don't want to, so I don't seem to be that excited about using Fourier's theorem. So probably Dirichlet, right? Then I don't have to worry about the weights. The weights simplify a lot of the analysis, but if we can get away without using the weights, that's a little bit nicer. So let's say f is continuous and decays like x to the minus alpha for alpha greater than 1. As do f prime and f double prime. So I'm going to just make some assumptions right now about the first two derivatives. I'm going to assume the derivatives also have decay. Now let's look at f of x is the sum and goes from minus infinity to infinity of f of x plus n. Okay, this is periodic on 0, 1. Is it continuous? And let's just.
I want to say yes.
I want you to say yes.
If f is continuous.
We're assuming f is continuous.
Yeah, right. Yeah. Because you can bound like f of x. You could say f of x is like epsilon close to like f of x plus delta, and like I'm sure you can go through it.
So I'm not going to bother going through it because what do you think I want to show after we show that it's continuous? We actually get uniformly continuous for free because it's periodic. Nope. If we want to use Dirichet's theorem, right? What's the ante to use Dirichet's theorem? Differentiable. So what do you think I'm going to want to show after we show it's continuous? Right. So given that we're going to show that it's differentiable, the same argument would have also shown that it's continuous. So I'm not going to bother showing that it's continuous. If we can show this now, then we would know that f of x is equal to the sum minus infinity to infinity of f hat of n e to the negative 2, e to the 2 pi I n x, where big F hat is the Fourier transform on 0, 1, or minus a half a half.
Well, we just assumed f is differentiable, right?
I'm sorry?
We already assumed f is...
We assumed little f was differentiable.
Oh, right.
We don't know big F. We now have an infinite sum. And you always have to be careful with infinities. So as an example of danger, let's let f of n be the following. It's 0 everywhere. And then here's 1 over n. Here's 1 over n plus 1 over 4n. Here's 1 over n minus 1 over 4n. So this is going to have width 1 over 2n. I just want to use a different number. And so this is going to have a width 1 over 2n. So let's go up to height 4n. What's the area under this triangle? One. Because the width is 1 over 2n, the height is 4n, and so I have 1/2 base times height. So the integral from 0 to infinity of fn of x dx, take the limit as n goes to infinity, this is always equal to 1. Right? So unlike the other example, here it's 0 everywhere else. Now, let's take the integral of the limit. Let's switch the order. So if I take the limit as n goes to infinity at any point x, what do I get? So now you choose some point x and get very, very large. What does fn of x go to? So what happens as n gets larger and larger and larger? What does fn look like? It gets taller, but where does it get taller?
0.
Is it at 0? What is fn of 0 for all n?
It gets taller at x equals 0.
What is the value of fn at 0?
Oh, it's 1.
No. Here's 1 over n. Here's 1 over n minus 1 over 4n. Here's 0 over here. What's the value of this function at 0? It's always 0 at 0. I then move a very small distance away from 0, and then I crank up, crank down, and then I'm identically 0. Think of it as you have a triangle which is getting steeper and steeper, narrower and narrower, and it's moving towards the origin, but it never hits the origin. If I evaluate x at 0, I get 0. Choose a value of x that's not 0. Eventually, n is going to be so large that your x is less than 1 over n plus 1 over 4n. Right? So what's 1 over n plus 1 over 4n should be 5/4 1 over n. So 5/4 1 over n less than x. That means once n is greater than 4x over 5, f of x equals 0. So you give me any value of x, and I can choose, oh, I'm sorry. It should be 5 over 4x, sorry. You give me any value of x, and once I choose n sufficiently large, the value of my function at x is 0. So if I look at the pointwise limit, what do I get? What's this limit at every value of x? 0. And we know it's 0 at 0, so this is just integrating 0. That's the easiest integral we can do. The limit of the integral is not the integral of the limit. All of these integrals are finite. There's no negative signs that go on. But what's happening is the function is getting extremely large at a point. And so there's a lot of results in analysis where you have to be very careful when infinities are in play. If the function were bounded, then we could switch. But because of the fact that it's exploding, we have to be careful. This is why I'm trying to motivate why we have to be so careful in the analysis we're doing. It's not clear when we write these things down that the sum exists. It's not clear that the derivative exists. It's not clear that the derivative is what we would expect it to be. We have to prove all these things. But if we could prove them, then we'll be in great shape. Okay, so what we have now is we would have Dirichlet's theorem if it's differentiable. So this is true if big F is differentiable. Okay? Let's assume that the function is differentiable and look at the consequences. And then we'll go back and prove that it's differentiable. Does it seem reasonable that the function is differentiable? Because I'm assuming both f prime, and f double prime are decaying rapidly at infinity. I'm assuming f is continuous. I'm assuming we have rapid decay. Based on all those assumptions, this should probably be differentiable. And if it's differentiable, then we can use Dirichlet's theorem. And Dirichlet's theorem says we have this pointwise convergence. So I hope you see that at this point that because we've put in a lot of assumptions about f prime, f double prime, we should be able to take derivatives.
So, and we can show that quite easily, right? Because it would just be the sum of f prime x plus n.
But then you need to show that that sum.
And like since we know that decay is like x to the minus alpha, we know it will converge.
We have to be a little bit careful. I think we actually do need something about f double prime as well. Because we need to show that it's differentiable and the derivative equals what we expect it to be. Now, if you had to guess what the derivative is, you would just put a prime by all the f's and say, come on. The only possibility is that the derivative of the sum is the sum of the derivatives. But that's not always true. We're switching operations. If it's finite switching, we can do finite switching without too much fear. But whenever there's an infinity, we have to be extremely careful in switching. So do people want to prove that the derivative exists first, or do people want to see the consequence first? First loud voice wins. Consequence, okay. So what does this mean? We have this formula here. You get to choose any value of x. A specific value is screaming, use me, 0. Right? Because if we take 0, we don't have to worry about these exponential factors. So at x equals 0, we get this. We get f of 0 is the sum, negative infinity to infinity, of f hat of n. Well, we know what f of 0 is. F of 0 is just the sum, and goes from minus infinity to infinity, of f of n. So all we have to do is show that this sum over here is basically the sum of the Fourier transform of little f. Okay, so let's see what we have now. So we have f of 0 is the sum, and goes from minus infinity to infinity, of f hat of n. So what is f hat of n? It's going to be the integral from 0 to 1 of f of x e to the negative 2 pi I n x dx. Okay. What does f of x equal? So we have a sum. Okay, so what does big F of x equal?
The sum of little f over x plus 9.
So can I write it as x plus n?
X plus n.
Yeah, we have to do a different variable because, so now we have an infinite sum followed by an integral from 0 to 1, followed by m goes from minus infinity to infinity of little f of x plus m e to the negative 2 pi I n x dx. Whenever you see expressions like this, you always want to interchange orders or piece things together. If you put in absolute values, everything is going to be fine and it will converge. I'm going to be a little bit careful. So let's look at just this part over here. We have a sum from minus infinity to infinity, integral from 0 to 1. I claim this is the same as the integral from minus infinity to infinity of f of x e to the negative 2 pi I n x dx. So x ranges from 0 to 1, and then you add m. So if you wanted x to be between 3.5, you would take m equals 3, and then you take the x equals a half. So this is going to hit all the numbers once and only once. I'm just basically splitting this integral up. I'm just combining it. And if you take absolute values, because f has decay, this is fine. So now we have this equals the sum, n goes from minus infinity to infinity. So we've just pieced the integral together. What does this equal over here? F hat. So this is now the Fourier transform of little f as a function on minus infinity to infinity. And so now we get the sum, n goes from minus infinity to infinity of little f hat of n. And this was equal to the sum, n goes from minus infinity to infinity of f of n. So that's the Poisson summation formula. It's a nice consequence of Dirichlet's theorem. We're going to see how important this is in Benford's law. And it all comes from being able to construct this function big F and apply Dirichlet's theorem. Now, to use Dirichlet's theorem, we do need to know that our function is differentiable. So hopefully now we've been sufficiently motivated to now roll up our sleeves and do the hard analysis. So these are things that you have to do once in your life. Once you've proven Poisson summation, then you can use it. And it's an extremely powerful tool. And in fact, one of my general exam questions was, why is the Fourier transform defined the way it is? It's so Poisson summation is nice and you don't have factors of 2 pi floating in that. If you had a slightly different definition of the Fourier transform, you would have to have a little bit of bookkeeping there. So all that's left now is to prove differentiability. Okay. Differentiability. Okay, so we want to prove that this is differentiable. All right. What is our candidate? If you had to guess what the derivative would be. The sum of the derivatives. So technically, I should introduce another letter, maybe g of x, and have it as the sum of the f primes. I'm not even going to bother. I can't do that with a straight face. I'm going to write as big F prime of x as the sum, and goes from minus infinity to infinity of f prime of x plus n. Does this sum exist? Does that sum converge? Yes, because we're assuming f prime decays sufficiently rapidly. So the fact that f decays means big F exists. The fact that f prime decays means this exists. Now we need to show that the limit exists, that the derivative exists. So we want to look at big F of x plus, I just want to use the same notation in the book. I think I used a delta. The delta, yes. X plus delta minus big F of x over delta, and then subtract off f prime of x. So we'll study this quotient and then take the limit as delta goes to 0. And we need to just show that this quotient goes to 0, and if it does, then that will justify that this is the derivative. And again, yes, if you want, you can call this something maybe g of x right now, because we don't know, but we have a strong belief that this is going to be the derivative. All right. So let's look at this. So we get it's going to equal f of x plus delta minus f of x over delta. So we're going to have a sum, and goes from minus infinity to infinity, of f of x plus delta plus n minus f of x plus n over delta minus f prime of x plus n. Do we all agree that that's the quantity we need to study? Okay, so what we can do is we can break this up into two parts, into small n and large n. So this would be the sum n less than or equal to n of f of x plus delta plus n minus f of x plus n over delta minus f prime of x plus n plus the sum over n greater than or equal to n. All right. So we break it up into two parts. And then we want to choose the big N so that the first part is small and the second part is small. All right. Well, let's look at the first part. When we look at this difference, we can approximate this using the mean value theorem. This would be approximately f prime at some intermediate point times the difference between them. So the first piece, the sum n less than or equal to n, is going to be the sum n less than or equal to n